as Gabriel says, what I'm going to talk to you about today is gamma ray spectroscopy at WIT. So just to put it into a little bit of context, why am I talking to you about this? Well, as Gabriel says, we do some research in this area, but in addition, we use our gamma ray spectroscopy system for a lot with our undergraduate students, albeit at final year level, where I teach on a nuclear and particle physics module with Cormac, who's our next speaker, and we have developed a program of experiments using the gamma ray spectrometer that is a very nice way to do the active learning that we like to talk about. So I do a lot of the nuclear physics theory and concepts, which sometimes the students might find a bit challenging, but then we actually get to look at it in practice because there's an awful lot of nuclear physics and indeed some results from relativity that we need to take into account in order to understand the subtleties and the intricacies of the spectra that we get from gamma ray spectroscopy. I don't intend, nor do I have enough time today to talk about the subtleties and the intricacies, so you'll be glad to know, right? Instead, what I'm going to do is just to give you an overview of this area and what we do here at WIT. I am mindful of the fact that those of you, and many of you are teaching physics at Leaving Cert, so I am mindful that there is quite a significant amount of nuclear physics on the Leaving Cert syllabus, or course, or I forget, let me think, was it specification? Thank you, that Jerry used earlier. So I'll try to link it into that. So I'm going to talk about what are gamma rays, the nature and the origin of gamma rays, how they interact with matter, which is very important for indeed any type of a detection system. So this spectroscopy system effectively consists of a detector of gamma rays. It allows us then to be able to quantify various samples and determine how much of a particular radionuclide that happens to be a gamma ray emitter, how much of that, and indeed perhaps numerous radionuclides are in a particular sample. Our main focus here at WIT is in environmental radiation monitoring. So there are many, many types of instances and applications where one might be interested in measuring the concentrations of gamma ray emitters, but I'm going to try to confine this mainly to talking about environmental samples. We look at some typical spectra, talk about some of both the undergraduate and the research work that we do here at WIT, and just a little bit then on future work. So just to begin, you should be I presume everybody is familiar with the electromagnetic spectrum, and the electromagnetic spectrum here, you can see the various regions and they're classified according to wavelength. So we have up here the long wavelength end, down here we have the short wavelength end, and in terms of energy, remember energy is h times f or hc over lambda. H is just Planck's constant, c the speed of light, and lambda wavelength. So we can very easily convert the wavelength into energy. The units that we tend to use in when we're talking about gamma rays are electron volts. You'll be familiar with electron volts. So typically the kind of gamma ray energy range that we're concerned with or interested in is from about 10,000 electron volts up to 10 million electron volts. So 10 keV up to 10 MeV. The gamma rays then are the extreme high energy end and high frequency end of the electromagnetic spectrum, and they're very close to the X-ray region. Where do these gamma rays originate from? Well, they originate from many different sources. Radioactive decay processes involve an unstable nucleus. So, So down here we have a nucleus. So in our nucleus we have nucleons, neutrons and protons, and there are various forces at play within the nucleus. If there's an imbalance between the electromagnetic force and the strong nuclear force, then a nucleus that is unstable wants to get rid of some energy. It can do this by emitting alpha particles, beta particles, or gamma rays. Gamma rays are photons, they carry energy away with them. So when a gamma ray is emitted, that means then that a nucleus gets rid of some energy and therefore decays, we say, to a more stable state. Gamma ray emissions usually occur with or almost immediately after an alpha emission or a beta emission. There are many radionuclides. When I use this term radionuclide, that means an isotope of an element that is radioactive, so it's a radioisotope, and in addition then it has a specific atomic number and a mass number. So for example, with uranium, you have the uranium-238 radionuclide and you have the uranium-235 radionuclide. Okay, so unlike alpha and beta radiation, gamma rays don't have any mass because they're just a photon of energy, nor do they have any charge. And this can make it difficult to detect them. Here, this is just showing some other sources of gamma rays. We can have gamma rays produced as products of fission reactions, fusion processes. So quite a lot of high energy astrophysical events will result in gamma rays. Here we've got a solar flare that will emit quite a significant amount of high energy gamma rays, and down here we have a gamma ray burst. I'm just putting those in because they're very nice pictures, but again, we don't do anything about this here. We're interested in environmental radiation monitoring. So just to see then a typical example of a gamma ray emitter, this is a radioisotope that is used a lot in medicine. So it's a man-made or an artificial radionuclide. Many of you might be familiar with cobalt-60. Cobalt-60 decays to nickel-60. So the mass number remains the same through a beta decay process. The mass number remains the same, and the atomic number here increases by 1. Most of the time, almost 100% of the time, it's via this process here. So it decays to, we call it an excited state of nickel. The asterisk here indicates that it's an excited state. That just means that the nucleus is in a high energy state. So after the beta decay, and this is what we call beta minus decay, there exists beta plus decay as well, the nucleus can try to achieve a more stable state by the emission of a gamma ray. And in the case of cobalt-60, it does this. This gamma ray is still in an excited state, so it emits a second gamma ray. Many radionuclides will just emit a single gamma ray, and sometimes there may be 2 or indeed more gamma rays emitted in what we would term a cascade of emissions. These gamma rays can interact then with material and we can detect them. So we need to have some sort of an interaction occurring. There are 3 main types of interaction processes: photoelectric absorption, you will know the photoelectric effect, Compton scattering, and pair production. Very briefly, because I don't want to spend too much time on this, for low energy gamma rays, they can interact. So this is an atom in some material. The material in the detector that we have is germanium. It's what's called a high purity germanium detector. So this could be an atom of germanium. A low energy gamma ray then it's incident with an inner shell electron. Here transfers all of its energy to the electron. That electron is ejected. Other things can happen as well, but we're not interested in the other things for now, right? If we have then a medium energy gamma ray, a medium energy gamma ray can interact again with an electron in the target atom. The target electron is at rest, but this time not all of the energy is transferred to the electron. Some is transferred to the electron, so we have a recoil electron, but the original gamma ray remains and it becomes what we call a scattered gamma ray. So we have a scattered photon here. Gamma rays can be scattered through a range of angles from 0 to 100 degrees, and this effect was first discovered by Compton, and it is termed Compton scattering. And finally, the third of these processes is pair production. This occurs, or is the most probable interaction event, for high energy gamma rays. So here we have the high energy incident gamma ray. In this case, this interacts very close to the Coulomb field of the nucleus itself. And if the energy is high enough, greater than this value, I'll explain the significance of this value in a few minutes, it can create a pair, and the pair is an electron-positron pair. Again, note we have an electron. A positron is simply the antiparticle of an electron. It has the same mass, but it has a charge of plus E. That positron can subsequently, that can be relatively short-lived. It's quite likely that will interact with the free electron and in an annihilation event create 2 more gamma rays. So there's actually a lot of things going on here. This original gamma ray disappears. We create an electron and a positron, but then subsequently, and in order to conserve momentum and energy, these 2 gamma rays must travel in opposite directions. The energy required in order to create an electron and a positron is going to then be equal to the rest mass energy of an electron plus the rest mass energy of a positron, which in both cases is the same. It's 511 keV. Multiply that by 2 and you get 1.022 MeV. So it is only gamma rays that have energy, that have enough energy in order to create an electron and a positron that can interact with the material through the pair production event. In order to detect gamma rays, then we need to have some type of detector. You will be familiar with Geiger counters based on the Geiger-Müller tube. Other common detectors include ionization chambers, sodium iodide, scintillator detectors, and then there are a whole range of relatively recently developed detectors called solid-state detectors. Within the solid-state family of detectors, germanium and silicon are 2 of the most, were 2 of the most important ones. There are, for some applications, silicon detectors may be the more useful ones. The one we have is a germanium detector. It has very good energy resolution. The gamma ray photons are incident on the detector. They interact via one of the 3 mechanisms that I've just outlined. You get electron hole pairs. Let's not worry too much about the detail of that, just that we get a signal, and the signal will give us a pulse. So we end up with a pulse, and the number of pulses per unit time gives us information about the intensity of the radiation, and this will allow us to ultimately determine the activity, which is like the concentration of radionuclides in a sample. So a typical spectrum then looks something like this. This is what we call the main full energy peak, or the photo peak, due to photoelectric absorption. You get this Compton continuum, and you see at the maximum point of this is what's called the Compton edge, and there are other features as well on the spectrum. So at WIT then, we've been, I suppose we installed the gamma ray spectroscopy system about 5 years ago, and we have been using it, as I said, for a series of experiments on our undergraduate physics program. So we tend to get or look at spectra like this. So what you will see here, I hope, is that there's a main peak. Perhaps I'll go to this one first of all. The nice thing about this type of analysis is you have to do, in a lot of cases, very little sample preparation. So if any of you are involved or have done some chemistry and using some analytical techniques that involve an awful lot of sample preparation, you will really appreciate this concept of not having to do much sample preparation. This spectrum here is acquired by taking some potassium chloride, which, if you're familiar with it, it's a salt. You get it in a chemistry lab. We took a couple of 100 grams of this, put it into a sample container, literally leave it on the detector. Now, this one was left for over a weekend. Natural potassium contains about 0.01% of the radioisotope or radionuclide potassium-40, which is a gamma ray emitter. So we get this potassium-40 peak. This is a very high resolution detector. So this actually is a peak. But it's a very narrow, what we say, very, very well resolved peak. Other features on this spectrum include this little Compton edge here. I'm showing this because we've got very nice, well-defined peaks. This is another one that we look at routinely, is cesium-137 spectrum. Cesium-137, again, a gamma ray emitter. You can see the cesium-137 peak, a very well-defined Compton edge here as well. Just a quick run through some of the details. Way too much information here in this schematic, but it's the schematic that I had. So the detector is here. When in operation, the detector needs to be cooled to liquid nitrogen temperatures. So that's to temperatures of about 77 Kelvin. That is to suppress any background signals from thermal electrons, so that any signal we get, or these electrons that ultimately give rise to a pulse, are then due only to interactions between gamma rays and the particular sample of interest. So you can see here the detector sits in a container. This is a dewar of liquid nitrogen when in operation. And of course there's various electronics, and indeed in this case here, this is just a photograph showing the actual detector itself, which is located in W06. And I noticed that some of the workshops this afternoon are taking place in adjacent labs. So should anybody be interested, I can show you the detector. So the detector is located in here. So this is the detector, this is the liquid nitrogen dewar. So when in operation then, on a weekly basis, we have to pump over liquid nitrogen from a detector that's over here, or excuse me, a dewar that's over here somewhere into this dewar. And there is lead shielding around here. This is just to suppress or try to minimize any of the background gamma emissions that exist in the air. And this is a top-loading system. So you just open this up, and these are two of the fourth-year students that posed for this photograph for me only yesterday. And this is just showing, this is a seaweed sample actually that we used when we were doing some marine analysis, and you just literally just sit it down very carefully. You have to worry about reproducibility, of course, and lots of things to do with this, and trying to make sure that you always position samples in a particular orientation. There's an awful lot of information on this slide, but it is a very nice slide. I've borrowed it from the World Nuclear Association website, and just talking about background radiation, there are 4 natural radioactive decay series. 2 of them start with uranium isotopes. This is the uranium-238. This one here is a thorium series. And in rocks and soil on the Earth, there are a lot of traces of thorium and uranium. So if we were to take, which we've done, a sample of soil, put it into the detector, or some rock and put it onto the detector, we should be able to see some of the decay series here. So for example, here we have uranium-238 will decay. A blue decay here is an alpha decay, so it alpha decays in this direction. A beta decay is a little purple decay, and then a little red one is a gamma emitter. So you can see the red ones are gamma emitters, and if I look here at this is a background spectrum that we acquire. Every year we have to acquire a 12-day background spectrum as part of our quality assurance procedure. So we see here we've got potassium-40. By the way, I think every spectrum that I have ever analysed on this detector will yield a potassium-40 peak, because there's potassium in and around so many things. Indeed, ourselves, we also contain a certain amount of potassium. Of that, 0.01% is potassium-40. So we all actually have and emit a very small amount of gamma rays. So we see other things here from the natural decay series like bismuth and lead and so on. This I won't talk about because Gabriel is standing, and I haven't even started to talk about the environmental radiation monitoring. Oops, I apologise. A lot of the environmental radiation work we do is in collaboration with the EPA's Office of Radiation Protection and Environmental Monitoring, formerly the RPII. They manage Ireland's national radiation and air quality monitoring programmes and routinely measure radioactivity in the air, drinking water, in marine samples, and a range of foodstuffs. So one project that we have collaborated on with the EPA, and this was a project, a final year project on our undergraduate physics degree last year, was on air monitoring. So they operate a network of permanent monitoring stations that just look like this, where there's a little air filter here, and air is pumped through this for a week, and then the air filters are routinely monitored. The radionuclides of interest to the EPA are cesium-137, beryllium-7, and potassium-40. Cesium-137 is the big one. If you see cesium-137, that tells you that there's been some sort of a release of radiation into the air. And this is just showing a spectrum from Cahersiveen, which is where one of the air monitoring stations is. Again, our usual suspect, potassium-40, always shows up, but that can be used very nicely as a quality assurance marker. So if I ever think the detector is misbehaving, I can put in almost anything and see at 1461 keV, do I have my potassium-40 peak? And if it is somewhere else besides 1461, I know then I have to recalibrate the system. And calibration is very much non-trivial. That takes quite an amount of time, but if it isn't calibrated correctly, we can't then stand over the results. This here just shows beryllium-7, and these are particular results that we obtained. There are 7 stations where they investigate what are called low volume air filters, and this just shows some of the measurements we've taken. Beryllium-7 is what's called a cosmogenic nuclide, and the beryllium-7 levels should be the same all around the world. So again, that's quite a nice QA marker. Quite a lot of what we were doing on this project as well was trying to get the EPA to approve our system. So we were doing a lot of intercomparison work, and our results compared very well. We didn't record any cesium-137. Well, what that means is that our detector system cannot detect the minimum cesium-137 level it can detect is this value, and we didn't record anything. So all we can say is it's less than this. And potassium-40, we subtract potassium-40 by doing these background subtractions or corrections. I haven't time to talk about marine samples, so I'll go to the last slide, which is on our future work. We have an ongoing program of undergraduate experiments that the students do always enjoy. One thing that I seem to have gone through quite quickly as well is that we take a banana, mash up a banana, put it into a container, pop it on the detector, and guess where you get a peak? They're a very good class, Gabriel. They learn. This active learning is very good. And some students start to get alarmed, and they start to think that I'm going to give everybody the message, stop eating bananas, and I'm going to affect the worldwide banana industry. But in order to get any kind of appreciable peak, we need to leave the banana on for a considerable amount of time. But you do get a very well-defined potassium-40 peak. So it's just to make the point that there's a lot of gamma emitters in the environment, and part of this environmental radiation monitoring means we need to know what's there in the background, what we expect to see, and then anything unexpected. So a lot of this radiation monitoring work involves, particularly say for the air monitoring, being able to look and notice and use this as an early warning system in the event of any kind of a release. For example, like the Fukushima incident in 2011, or going back as far as 1986 to Chernobyl. We recently signed a service level agreement between WIT and the EPA. This will involve us acquiring a second one of these systems, which hopefully will be in operation in January. And this will allow us to provide additional support to the EPA, and we come in under what's called their NEPNA program, which is a National Emergency Plan for Nuclear Accidents. So that just gives you an idea of work that we're doing. We've also, we're waiting to hear on a funding proposal that we've put in collaboration with UCD, who have a similar facility to we have. So hopefully we'll be able to get to extend some of the work that we're doing into some future research projects. If anybody has any interest in gamma ray spectroscopy, these 2 books here are kind of the Bibles for this area, particularly the first one, and many of the diagrams and nice pretty pictures that I've used here are taken from these websites. So apologies for going over time, Gabriel. I know I'm going over time because he's standing there for far too long. And thank you very much. And apologies to Cormac.
Thank you very much.